Hi everyone, I'm Amanda, and I hope you've been enjoying learning about volcanology as much as I have this semester. And so today, what we're going to learn about is cryovolcanism. All right, so terrestrial volcanic eruptions are what scientists are most familiar with, especially those that are in populated areas. However, as Dr. Anderson mentioned earlier this semester, we do know that volcanism occurs in other parts of our solar system. And today I'm going to talk about a specific type of volcanism, the cryovolcanism. So here's an image taken by NASA of Enceladus's ice geysers, which we're going to get to later. But I think this is a beautiful image and we'll kind of get you excited for what's coming up next. Speaking of what's coming up next, here's our outline for today. So we're going to talk about what is cryovolcanism, what are the conditions that are needed for cryovolcanic activities to occur, what are the composition of these different magmas, what are the different eruptive processes, and where does cryovolcanism occur? All right, so if we think back to the beginning of the course, Dr. Anderson mentioned that we can think of water as magma, because if we think of what is magma, then we know magma is made up of melted rocks, and rocks are composed of minerals. And when we think of ice, we know that ice is a mineral, and when it comes together, we have now a rock, and if that melts, we get water. So we can think of different types of ice as different minerals, different rocks, and also then when we melt it, we have created different magmas. So thinking about this, what I want you to do, and I'm going to give you about like 30 seconds, and I want you to think about how would you define cryovolcanism? Like what would your definition be, knowing what you know about magma and volcanoes? Mull it over for about 30 seconds. I'll give you some time. So. Alrighty, so let's compare what you all have thought about to. Alright, so Geisler 2015 defines cryovolcanism as the eruption of materials as liquids and vapors that would otherwise freeze solid at the planetary surface temperatures. And this definition is relevant as we're going to use this to determine on what different planets and satellites we see cryovolcanic activity. All right. All right, so where do we find cryovolcanism? Well, by the definition that we're using, we see cryovolcanism on icy satellites of giant planets, but we can also say that it occurs also on Earth and Mars. So we're going to talk about specific places and mechanisms of cryovolcanic activity in a few slides, so we'll get there. All right, so what are the conditions that we need to meet for cryovolcanism to occur? One, liquids are to be generated in the interior, and two, the melt has to migrate to the surface. So what this means is that we have to have a way of heating things. All right, so for liquids to be generated, we have to heat up those different ices. And so we talked about different ways in which we can cause heating. And there was one in particular that Dr. Anderson mentioned earlier this semester, that a type of heating that related to the different satellites and the different planets in our solar system. So I'll give you a little bit, look back in your notes, think about it, if you can remember what that heating mechanism is. All right, so if you look back in your notes, one of the main ways that we get heating is through tidal heating. And so this is the frictional heating that is caused when the satellite changes shape during the day. So if a moon is by other large planetary bodies and it's being pulled one way and pulled another, then this friction can cause heating. Another way is through radioactive decay, so the decay of radioisotopes. And also our third way is through gravitational heating, which is due to accretion, so as things are being accreted to, piled up on each other, and also differentiation, so as things are separating out due to density. All right, so other conditions we have to consider are our planetary factors. So what's the size of the planet, of the satellite? What's its composition? This is particularly relevant to the amount of silicates that are there, which will determine radiogenic heating. What's the surface temperature? How close is it to the sun? What's its location, which is related to composition and surface temperature? And what's its orbital history, which has to do with the amount of tidal heating that we have. And so our tidal heating is due to the daily distortions from non-circular or oblique orbits. So non-circular orbits are often created by gravitational interactions with other nearby satellites, and the orbital eccentricity over time is increased by the orbital resonance. So what this means is that if we take, for example, 3 of Jupiter's moons, Europa, Io, and Ganymede. So Europa is caught in somewhat kind of like this tug of war between Io, which is closer to Jupiter, and Ganymede, which is further away. So they have different orbits, and Io and Ganymede are pulling on Europa, which is changing its eccentricity and rising the tides on Europa, which may be causing the melting to occur and forming a molten layer of liquid beneath Europa's surface. So you don't need to know specifically eccentricity and orbital resonance, like those terms. More than anything, I just wanted to give you this visual idea of what's happening, how this friction is occurring, and how melting can happen. Oblique orbits. So what an oblique orbit is this is the inclination or the tilt of the satellite's orbit with regard to its equator. So this is usually caused from collision or capture. So as planetary bodies are hitting one another, or so let's say a large planetary body captures something like an asteroid, and now that asteroid has become a satellite. All right, so far we've talked about what is cryovolcanism, the conditions that are needed. So let's move on now to composition and eruptive processes. So beginning with chemistry, observations have confirmed that the dominant ice seen on satellites of Jupiter, Saturn, Uranus, and Pluto is the ice we're most familiar with, which is our water ice here. Methane and ammonia is also present surrounding Jupiter and Saturn, and other compounds such as methanol and formaldehyde have been observed in comets and may be present in minor components on these distant satellites. So I included this table just because I wanted to give you an idea of the different types of ices that can be present in our solar system and on these different satellites. So what's the evidence that we have that these satellites contain or may contain these different ices? One is direct spectroscope detection, but doesn't always work, and it only tells scientists about the uppermost surface of these different satellites. Scientists have also used the density of the satellites and their moments of inertia to attain gravitational measurements that give an idea of the interior structure and composition. And other valuable clues have also been attained through theoretical modeling of primitive meteorites, which are also called carbonaceous chondrites. So all of these have given scientists ideas of what these outermost satellites are made of. All right, so now we know more about the composition of our icy magmas. So now let's start talking about other components that are related to our eruptive processes, such as viscosity. So here I included a table to show the wide range of viscosities of these cryomagmas. So on the x-axis, we have the log of gravity, and on the y-axis, we have the log of density and gravity over viscosity, which is our mobility index. And what I want you to take away from this is that we have, some of these cryomagmas have a very low viscosity. This here is even lower than water, but some are just as viscous as dacite here on Earth. And if we remember back to when we talked about Mount St. Helens, dacite was the type of lava that is associated with that eruption, so it's quite viscous. Now, let's talk about some issues that we have. So, one I mentioned earlier is that the main type of ice that is thought to be on these satellites is water ice. And unlike silicate minerals and rocks, when ice freezes, it actually becomes less dense than the liquid. So what this means is that the water shouldn't actually rise up and through that icy crust. So then what do we do? How do we get eruptions to occur? Well, one idea is that and early in the history of these planets, before differentiation occurred, these briny magmas were more buoyant than even the silicate crust. And so it's believed that these magmas moved upward through fractures and faults, kind of similar to when we think about crevasses in glaciers on Earth. And so the briny magma would move up and pool and then sink down through the ice, and then the ice would close up behind it. So then this type of eruption process is controlled by gravity, and once differentiation was complete, then the process was over. It's also thought that on smaller satellites, the cryomagmas would descend more slowly, and you would have longer eruptions because they had lower gravity, so it would take longer than on other larger satellites. Another idea is that water, as we know, is a great solvent. So if you're to partially melt ammonia into water, this can help with the density issue that we have with pure water and pure water magmas. And so then this would make the magma more buoyant, and it could then rise up through the ice and erupt. Another idea is we have overpressurization. So, which can happen in the last stages as the satellites evolve and the subsurface liquid layer cools and freezes. And as the water expands due to freezing, the surface can fracture, and then the magma can flow out like in an artesian spring. It's also probable that some satellites like Triton's geysers, these types of volcanism is driven by superheating silicates or by solar installation, which can, I'll talk more about Triton in a minute when we talk about specific places where cryovolcanism can occur. So, and a last mechanism to cause eruptions would be the gas-driven. So, gas-driven volcanism is possible as volatiles are incorporated into the ice, and so this would make the ice like an icy version of Earth's pyroclastic eruptions. So all those gases get in there and get it ready, and then we get a nice big explosion. All right, so now let's talk about where do we find cryovolcanism. So we're going to start close to home, and then we're going to move our way out further into the solar system. And so if we think back to the definition we're using by Geisler 2015 on what is cryovolcanism, which is the eruption of materials as liquids and vapors that would otherwise freeze on the planetary surface. So by this definition, we can say that we have cryovolcanic activity here on Earth. An example of this is Lake Superior, and what happens in the winter are these features called ice foots. So as the waves that are forming in the open water, they push water through cracks in the ice at lake margins, and these icy mounds are created. So people have, by this, as I said, by our earlier definition, this has been defined as our cryovolcanic activity. Another example is the Yamal crater in Russia. So this crater is about 20 meters in diameter and about 50 meters in depth. And it could have been formed by other processes such as a meteorite impact. However, scientists also believe that this could be the result of cryovolcanic activity. So before I get into the process, let's go over a couple of terms. So our first term is a pingo. So pingos are areas where there's permafrost, and freezing groundwater creates enough pressure to push the ground up to make hill-shaped domes. And italic is a layer of body of unfrozen ground found in areas where there's permafrost. So what's been proposed is that a lake formed in this area underneath which there was this area of unfrozen earth. So we have our italic here, if you see this image here, underneath the lake. However, as the lake dried up and shrank, then this area of unfrozen earth underneath here would also shrink. And if we look down to our image C, we can see it's shrinking in, and then that pressure is going to start pushing up and creating the pingo, which we can get a better idea of that with here, this image D. But before freezing completely takes place, the idea is that a large amount of carbon dioxide, which is dissolved in water in the pore spaces of the rocks nearby, was released and built up. And as this gas just continued to build up, all that pressure is built up, it then caused the pingo to explode, and the crater that was left took the shape of what remained of that talc core underneath the ground. So that's another possible example of cryovolcanism here on Earth. All right, so again, by our earlier definition of cryovolcanism, we can also find cryovolcanic activity on Mars. So how this happens is that seasonal polar ice caps that are made of CO2 ice will erupt CO2 plumes when the ice sublimates in spring. So sublimates means that the ice will change from a solid to a vapor without going through a liquid phase. So in the spring, the ice heats to a point that it immediately turns to vapor, and we see these CO2 plumes occur. All right, so let's keep moving out into our solar system, and let's talk about Europa, which is one of the moons of Jupiter. So the first glimpse we got of this icy satellite was in 1995 by the Galileo mission. And based off of Europa's topography, it's thought that there's a subsurface sea under its icy shell. And this icy shell has gone through a lot of resurfacing. There are many ridges on Europa's surface, many different generations of these different ridges, ridge building events. And so there are different ideas on what's caused these different ridges and formations on Europa's surface. And I'm going to show you two different diagrams of these two competing processes. So first, we have the idea that diaprism caused these formed these ridges. So it could be that below the surface, the ice has been warmed enough to flow, similar to the glaciers that we see on Earth. And through diaprism and convection of the solid ice, it could be responsible for these ridge formations and other thermal disrupted areas. So the cold ice at the surface will be denser than the warmer ice below, and so this colder ice will tend to sink, and as a solid state convection takes place, the buoyant ice from below will come through fractures in the more brittle ice, and will create these ridges. The issue is that these ridges tend to form in pairs and be symmetrical and be uniform, and these sorts of formations are hard to explain by diaprism. So the second process that could explain these ridges is cryovolcanism. And it's possible that these ridges are formed as fluids are pumped through fractures in the crust that were created due to tidal heating. So as Europa orbits Jupiter, tides that are tens of meters high should rise each Europan day, which is about 3.5 Earth days. So for about half of the orbit, the planet's going to be pulled and we're going to get fractures forming. And through these fractures, we can get this slurry coming up and we get this being erupted onto the surface. While then the second half of the orbit, these cracks are slammed shut. And so that's one idea of how these ridges are formed in cryovolcanic activity on Europa. Another possible example of cryovolcanic activity on Europa was not sensed by Galileo, but recently the Hubble telescope may have detected atomic hydrogen and oxygen around Europa's southern pole, which could indicate that plumes of water vapor that can reach 200 kilometers in height are being erupted from Europa's surface. So it definitely seems that there's cryovolcanic activity and there's examples of cryovolcanic activity on Europa. All right, so I just wanted to do a quick slide about Ganymede, which is another of Jupiter's moons. And originally, scientists thought that cryovolcanism was occurring on Ganymede, and this is because the Voyager missions showed that the surface was smooth. However, the higher resolution from the Galileo missions showed that the surface was in fact grooved, which we can see here. And so this ended up changing scientists' minds, and these are not flow features that are issuing from fractures. And this resurfacing is actually thought not to be due to cryovolcanism, but to tectonic deformation. So I just wanted to include this to just, we as scientists, our ideas about things, information can change. And it very well could be that cryovolcanism is occurring on other planets and other satellites, and we don't know it yet. So this can always change. All right, so Enceladus is a moon of Saturn, and it's pretty small. Its diameter is only about 500 kilometers, which is the diameter of Olympus Mons on Mars. So it's a really small moon. So the northern hemisphere is believed to be covered by ice that has been somewhat cratered, but most of these craters seem to be dated back to about 10 to 100 million years ago, and nothing much seems to have happened in that area since then. However, the southern hemisphere has been documented to be much more dynamic. So the Cassini orbiter, which is active in 2004-2017 time, showed that the southern hemisphere, that region, is covered by a surface of ice that has been tectonically disruptive and has been interwoven with these light blue fractures. And this area is termed tiger stripes. And so we can see these tiger stripes here in this image. So the ice in these tiger stripes have been measured by infrared spectrometers to be about 15 degrees Celsius warmer than the surrounding ice plates. And this tells scientists that it's likely that relatively warm, probably liquid water, is active underneath the surface. So, all right, so Cassini also documented a 500-kilometer geyser shooting out of the southern hemisphere. And what's really cool about these geysers is that they're dispersing into Saturn's E-ring, so they're feeding this ring of Saturn. So that's pretty neat. And you can see here, let's see, This is our image of the geyser. So it's a really cool shot. So where are we getting the water for these geysers? And yet again, if we believe and we think that there is a subsurface ocean underneath the crust that is barely above freezing temperatures, and so this is probably where these the fluids came from to create these geysers. But then the next question is, how do we get this to erupt? And so I'm going to give you just a little bit, think about how do you think eruptions could occur on this moon? All right, now that you thought it over, there's actually kind of a bit of a debate. It could be that we're getting heating from tidal heating, and this is then a mechanism that's behind this eruption. It could also be that bubbles are forming as CO2 is dissolved, and then when fractures occur, this pressure is released, and then our geysers shoot out. And this, think about if you shake up a can of pop and then you open that up. It's that same sort of pressure release mechanism. So in 2005, the Huygens probe landed on Titan, which is a moon of Saturn. And images that were sent back showed features similar to what we might see on Earth, like dried riverbeds with boulders and cobbles. However, these boulders and cobbles are made of ice and were probably altered by methane rain. So methane at Titan's temperatures will act similar to how water will act on Earth, and so it will flow. And Cassini has detected different features such that resemble like glaciers and lava flows and ice shields and ice calderas. And in the poles, it's been detected that there are different lakes of methane and ethane, and particularly at the North Pole, vast lakes of hydrocarbons have been observed. And this image here was caught by an infrared camera on Cassini, and it's a very interesting phenomenon called a sun glint, which is a specular reflection off of one of the lakes in the north. So that's really cool, that the timing we were able to get that shot. So where are we getting this cryomagma? So it's thought that tidal stresses are causing warming and that there's a subsurface ocean underneath the icy crust. And although we're not sure how exactly these are been erupted, it's believed that these hydrocarbons were erupted from Titan's icy interior during past volcanic eruptions. Additionally, Cassini did radar mapping during 2 flybys of Titan in 2007 and took images of Ganesa macula, which is right here. And this is thought to be a possible cryovolcano on Titan. And these lighter flows over here to the right have been interpreted to be cryovolcanic flows. So for the next slide, I found a video on nasa.gov's website of these images put together by Cassini's flyover of Titan. I'm not going to talk through that. There's text that's going to walk you through what you're going to see in the image. It's in the images in the video. I think it's really interesting. And then we'll meet back up again when we start talking about Triton, which is one of Neptune's moons. So this is an image of Triton, which is a moon of Neptune. And what's really interesting about Triton is that it is the coldest and most distant moon that's been visited by spacecraft. However, it's the first place where volcanic venting was observed. So when Voyager 2 was passing by Triton in August of 1989, it was photographing the southern hemisphere, and it caught images of two plumes rising about 800 kilometers off of the moon's surface. And after shooting off of the surface, the plumes then collapsed and flattened out and spread about 150 kilometers downwind, and leaving behind these dark ejecta blankets. And Voyager 2 also noted that over 100 of these dark streaks were evident on the surface, and so evidence of earlier plumes. So the thing to understand about Triton's surface is that its temperature, its surface temperature, is negative 235 degrees Celsius, and gases such as nitrogen, carbon dioxide, and methane will freeze at these temperatures. However, nitrogen will sublimate, and I mentioned this term earlier. Can you think back? Do you remember what this means? Give you a couple seconds. Okay, so this means when we change from a solid to vapor, skipping the liquid phase. So nitrogen can sublimate and cause violent eruptions, and so the nitrogen will do this at negative 225 degrees Celsius, which is just above the average daily temperatures on Triton. And if we can get this to happen, then there will be a violent, the nitrogen gas will erupt violently if we can just heat up Triton's surface temperatures just a little bit. All right, so how do we heat up our nitrogen? Well, one idea that's been proposed is a solid state greenhouse effect. So the idea is that carbon particles that are trapped in the translucent thin icy crust will absorb weak sunlight, and then will re-radiate this energy out as thermal infrared wavelengths. And this is what's been heating the nitrogen. And once the nitrogen sublimates, it will expand with a lot of force, about 100-fold per unit volume. And this is potentially how we got those plumes to form. So what's really great about the timing of Voyager 2 as it was passing Triton's southern hemisphere was that the area was nearing its summer solstice, which would be a great time for this type of heating to occur. And considering that a year on Triton is about 165 Earth years, this was really good timing, that Voyager was able to pass the moon and take images and document these eruptions. So Voyager 2 also took images of other possible evidence of ancient cryovolcanism. So this lower image here shows two possible caldera-like formations on Triton's surface. And the larger image here also documents possible cryovolcanic activity. So the area in the upper left has been named the Cantaloupe Terrain, which is made up of semicircular depressions and that are bounded by ridges. And these flow-like features may have been caused by earlier cryovolcanic material flooding and covering the topography of the area. And it's also been suggested that these features could be due to diaprism and possibly a solid state convection in the interior of the moon. Very beautiful terrain nonetheless. All right, so I'm going to end today with a quote by Lockwood and Hazlitt. Even if we can't be sure that life exists on other worlds, we can be sure that volcanoes do. Well, I hope you enjoy learning about cryovolcanism today, and there's a couple more slides that have my references if you're interested in looking anything up. I highly suggest going on the NASA website. There's some really great images, some really great information on there. So thanks everyone.